This video describes an experiment to measure the terminal speed of a sphere falling through a liquid. Now, when an object falls through a fluid, that could be a gas or a liquid, the object accelerates until it reaches a maximum speed that we call its terminal speed or terminal velocity. This is true for raindrops, volcanic ash, or a free-fall parachutist falling through air, or a stone falling through water. Bubbles of gas rising through a fizzy liquid also have a terminal speed, and you may have noticed that big bubbles rise faster than little ones. And just let's think about raindrops for a moment. Their terminal speed also depends on their radius, of course, and the density of the water and the air. This means that big raindrops fall faster than small ones and so hurt you more when they hit you. For our experiment, I'm going to use a small ball of plasticine and I'm going to let it fall through wallpaper paste that I've got in this plastic bottle. The ball has a diameter of 8 millimeters and a mass of just about 1 gram. And as it falls, we're going to time its motion between the two rubber bands that I've fixed round the plastic bottle, and they're exactly 15 centimeters apart. Now, in case you want to try this yourselves, the wallpaper paste has been made with 15 grams of powder in 1 litre of water. Now, we must allow the little ball to accelerate a little bit to start with until it reaches its terminal speed, which is why timing will only start when it reaches the upper band and finish when it reaches the lower band. Before we do the detailed measurement, I'd like you just to have a look at 2 balls of plasticine, one with the mass of 1 gram and one with double the mass, i.e. 2 grams. And I'm going to drop them both one after the other and see how they move. Ready? This is the little one. You can see it sinking slowly through the wallpaper paste. All right, now here is the bigger one. Ready? Here it goes. And you saw that that was a much more rapid motion. The larger one goes much faster than the little one. Right, so now let's do the proper experiment. To measure its speed, all we need to do is to measure the time it takes to fall the 15 centimeters from the top rubber band to the bottom rubber band. So I'm going to do this by upending the bottle each time and using the same ball. So here we are ready to do run number 1. And you can see the ball beginning to fall down, and we'll start the timing now as it passes the top rubber band, and we'll stop the timing when it crosses the bottom rubber band. That's making a very nice steady run down there, and we'll stop it when it crosses the band there. That's 14.53 seconds. Reset the timer and now simply upend the bottle and be ready to do run number 2, which starts there. I don't know whether you can see the ball particularly well. There it is. That's a better view of it for you. And it's reaching the bottom rubber band there. 14.51. Well, that's remarkably close. I suspect that is just luck. Okay, and we're now ready to do run number 3, like so. And the ball's on its way, and it's crossing the first rubber band there. And we'll just turn the bottle around again so you get a good view. There it is. And stop there. 15.29, and we'll do 1 more run and then take the average of the 4 runs. So upend the bottle, get ready to start timing now. You may not have seen that one as well as I did, but there it is. It's going down here. And stop. 15.49. Well, let's put the bottle back. So that was 15.49. And I've now got to add up the 4 readings and we'll take an average. So 14.53 plus 14.51 plus 15.29 plus 15.49 equals 59.82 divided by 4. That gives 14.955. Well, quite honestly, we could call that effectively 15 seconds. And that's really rather nice because the ball has fallen 15 centimeters in 15 seconds, and that means a speed of 1 centimeter a second. So we have calculated the terminal speed for this ball in this wallpaper paste as 1 centimeter per second. Now, I said earlier that the speed depended on the radius of the ball and the density of the solid and the liquid, but it also depends on a property of the fluid called its viscosity. This is the property that makes syrup flow much more slowly off a spoon than water, and we can work out the viscosity of our wallpaper paste using the following formula. Now you see it on the screen in front of you. The viscosity of the liquid equals that formula. Now, I took some readings earlier off camera and got an average terminal speed V of 0.96 times 10 to the minus 2 meters per second. Now, the density of the plasticine rho was 2,290 kilograms per cubic meter, and the density of my wallpaper paste, sigma, was 1,015 kilograms per cubic meter. The radius of the ball, r, was 4 times 10 to the minus 3 meters, and the acceleration due to gravity, g, we will take as 9.81 meters per second squared. Therefore, using the formula for the viscosity of my wallpaper paste, we get a value of 41 Newton seconds meter to the minus 2. Now, for comparison, the viscosity of syrup is 100 Newton seconds meter to the minus 2 at room temperature, while the viscosity of water at the same temperature is 0.001 Newton seconds meter to the minus 2. So our value of 41 for the wallpaper paste seems quite reasonable.